Okay, morning everyone. We're going to start. So last lecture we talked about why depth first search is not a suitable algorithm for our milestone tree, and we talked about breadth first search and how it works by basically visiting wavefronts one at a time and expanding that wavefront. So we showed at the end of the lecture that I'm gonna go over it in a bit, that the breadth first search right now as we implemented it, does not take into account the travel times of the street segments. So we cannot optimize for the optimal solution that we want, which is the minimum travel time, the path that achieves the minimum travel time. So we showed this example where we start at the source 0 here and our destination is at 4. And first we populate the wavefront with node 0, which is intersection 0, and then when we visit it, we mark it as visited, and we push to the wavefront 1 and 2, because these are the neighbors of node 0. Okay, and after that, because node 1 was pushed first for some reason, we pulled node 1 and marked it as visited, and we marked that it came from edge A, which takes around 15 seconds. Okay, so after visiting node 1, we push node 3, and now we are visiting node 2. Node 2, we mark it as being visited from node B, we mark it as visited, and we push node 1 again to the wavefront because node 1 is a neighbor of, or intersection that we can reach from node 2. Okay, now we pull node 3, mark it as visited, mark it as coming from edge D, and then we push node 4 because it's a neighbor of node 3. And now we pull node 1 again, but we don't do anything right now. Why? Because we already marked it as visited, so we don't bother visiting it again, and we just remove it from the wavefront, right? And finally, we visit node 4 and we get our path, which is this path. But if you look at the overall travel times, this path is taking 15 plus 9, which is 24 seconds, while this can achieve 5 seconds less if we went through node 2. Okay, so we found a path, but it's not the shortest path, and that's a problem with breadth first search, because as is, it considers all edges in the graph as equal, right? So it doesn't differentiate between those edges, and it will eventually find a path. If all of the edges are equal, then it is guaranteed that the path found is going to be the minimum travel path, but in our case, it's not the case. Okay, so we need to do something better. One way to fix this is to, instead of marking nodes as visited, we try and revisit them again if we found a path that reaches that node in a better way. Okay, what do we mean by that? So at each node, instead of storing the Boolean flag visited, we store the shortest travel time from the source to reach the current node that we've found. So we initialize this variable for each node to like some maximum value, and while traversing the graph, we start one by one checking if the travel time to reach that node is less than the current travel time. Okay, so if it is, then we reprocess that node as if we visiting it for the first time, and we continue traversing all of its neighbors or all of its children. Okay, so here is the example again. Here we are pushing node 0. After visiting node 0, notice here we're not marking nodes as visited anymore. We will just update that the travel time to reach that node is this much. Okay, since this is the source, the travel time to reach this is 0, right? And now when we pull node 1, we mark the travel time to be 15 seconds, because this is the best travel time that we found so far. And we push node 3 to the wavefront. Okay, after visiting node 2, we mark the best travel time to be 5 seconds on it, and we push node 1 again. Then we push node 3, okay, that's 21 seconds. Okay, and then we push node 4, and now we are visiting node 1 again. Okay, so when we visit node 1 again, we find that the current travel time to reach node 1 is 10 seconds, which is less than the best travel time that we found for node 1. So we re-expand from there, and we don't throw it away as we did before. Okay, so we push node 1, we pull node 1 and push node 3 again. So visit 4, it will mark it as 24 seconds because this is still the old travel time. Then we pull node 3. We found that, okay, with node 3 right now achieves 5 seconds less, so we're going to update it and expand again, push node 4 again, and we achieved we got node 4 with 19 seconds. Okay, so this is the best travel time we can reach node 4, and we guaranteed that by revisiting the nodes whenever we find a better travel time. Any questions on that? Okay. So, yeah. So to do that, we need to store more elements or remove some of the elements that we defined in the data structures that we provided, we introduced last lecture. Okay, so remember this wave element data structure where we used it to populate the wavefront, right? We defined the wavefront as a linked list of all of these elements. So initially we had only two things defined on it. The node ID, which is the current intersection ID that we are at, and the edge ID, which is the edge ID that we use to reach that node. Okay? Now we add to it another member variable, which is the travel time. This is the travel time that we calculated to reach that node starting from the source. And for convenience, we define this constructor where we define the node ID, edge ID, and the travel time, current travel time. Okay? Then there was this another class node or struct node that we used to store all of the information about the path traversals globally. Okay, so initially it had information about who are the outgoing edges from the current node. Okay, obviously it has the intersection ID that we're at, and it has the street segment index or the edge ID that we use to reach that node, right? So this is used after the breadth search to backtrace and find the actual path. Now we add to it another variable which is called the best time. And this is the shortest time found to reach this node. And this is stored globally so that we can visit it later. Now some students are usually confused why we need to define two travel times or like two structs. Again, one is used to do on-the-fly work, which is while doing the breadth first search, we are trying to populate the wavefront and depopulate it. So we use this. While this is to store things globally and to be able to visit them later when we do the backtrace. Yes?
So every time you update your best time, you also have to update your reaching end, right?
Yes. So every time you update the best time, we know that we can achieve, we can reach that node in a less time from a different edge, right? So we have to update that edge in order to be able to backtrace properly at the end of the algorithm. Okay, any questions? Oh. Okay, so let's modify the algorithm a little bit. This is the same pseudocode that we showed last week instead, but we have a little bit difference here in how we're traversing or how we're looping over the nodes. Okay, so initially, whenever we found the path, whenever we reach the destination, we just return true. That means we found the path, right? In this case, we don't do that because we might need to re-expand later on and if we found a better travel time. Okay, so we define this path found Boolean, and we keep looping. Here, initially we just loop until the wavefront is empty, right? Here we keep looping while we might have a better solution, which is kind of the same. It's probably the wavefront should not be empty, right? And whenever we depopulate the current node, what we do is we check if the travel time of the wavefront, of the wave element that we are at right now is less than the best time for that node, for the current node ID, then we found a better solution and we need to re-expand from there. Okay, so first we update the reaching edge. Remember, we initialize all of these best times to some really large number. So initially all of them have infinite travel time. Okay, so we update the reaching edge to be the edge ID of that wave element, and the best time to be the current travel time of that wave element. Okay. If the current node is equal to destination node, we mark this Boolean as true, but we do not return. Why? Because we might need to re-expand. Okay? Then we visit all of the outgoing edges of the current node ID similar to what we did before. And when we push back the node, the neighboring node ID, the edge that we use to reach that node ID, and the new element here is currently whatever the best time that we achieved on the current node plus the travel time of the outgoing edge. Now we're not taking into account the turn penalties, right? In milestone 3 you have this turn penalty metric that we have to take into account. It will make it a little bit more challenging, but it's still kind of the same concept. You will need to update the travel time to reach that node. Okay, so the best time plus the travel time, this is usually get it from one of the methods that you implement in milestone 1 to get the travel time of a street segment. Yes? Previous slide, yeah.
I also have a question with the two structures. Isn't that the node structure from the bottom one you showed in the previous slide? Was referring to like the global variable where we're setting that node's best travel time?
Yes, so we have a vector of all of these nodes, and they are usually indexed by the intersection ID, right? And that's the global data structure that you will use later on to actually construct the path.
Yeah, so then you're using the wave elements to go through the specific path, right?
We use the wave element to traverse the whole graph during the algorithm. So when we do things on the fly, because we construct these elements and we destroy them later on once we visited them, right? So we don't care about them. But for the global data structure, we have to keep them to keep them alive throughout the whole algorithm, and that's why we put them separately and try to update them.
But then after you're done with that path, don't you need to clear whatever you change in the global vector? Let's say you have like a certain time set, but now someone has a completely different path. Then that time.
But that's what we're doing here. So if you look here, if we found a better travel path, we are updating these global variables.
Yeah, and I'm saying after you're done with this specific path, don't you need to now erase everything for the next iteration? Because you'll have best times for certain nodes, and it might not make sense to give a completely new path.
No, but that's what we are trying to do. So it's a global data structure, right? It's initialized to some very large value for each node, okay? And in each iteration, we are visiting nodes, right? We don't know what the nodes that we are visiting, right? But we are indexing them through the current ID. We take that. If whatever value is stored on that node right now is greater than the current travel time that we are able to reach that node, then we update it. We don't need to clear it because we are guaranteeing that at each iteration of the loop, this is the best time that we can have to reach that node right now. But when we finish the whole algorithm, the whole method of breadth-first search, we are guaranteeing that this is going to be the minimum travel time because we cannot visit that node again from any other edge. We've consumed all of the possible combinations that we use, or that we can have to reach that node.
So you're saying that someone searches out the first path, and let's say the current edge is A, and it's a certain time.
Yeah.
Now if someone has a completely different path they search up,
Yeah.
and it involves that node, and it goes back to A, but your path doesn't involve A, that would still work?
Yes, and you can see it from the previous example. We can go back to this example, right? So initially we visited node 1 through A, right? So through this edge A. And we updated the node data structure to say that the best travel time to reach that node now is 15 seconds, okay? And then we continued traversing the graph, different iterations. We pulled 2, and we noticed that 2 has an outgoing edge that goes to 1, right? So we calculated the travel time to 2 to be 5 seconds. And then the travel time to go through 1 from 2 is 5 plus 5 is 10 seconds. So when we visited 1 again, we checked that the current travel time that is stored in the node data structure for 1 is 15 seconds. But this 10 seconds is better than that path, right? So we update the reaching edge of node to be C. Okay, so after we traverse the whole data structure, we see that the path that we found, 1 is coming from C. Okay, and that basically guarantees to us that this is the best travel time to reach 1. Does that make sense? Okay. So once we visit all of the edges, we keep looping over all of the different nodes in the wavefront until we are out of nodes, or until we are out of nodes. If then we return this Boolean flag. If we didn't find a path, then the path doesn't exist. Otherwise, we definitely found a path, and you should visit the node data structure to backtrace and find the path as we did in the previous lecture. Okay, so let's talk about complexity. So forget about the how we fixed it, right, with the expansion. Let's talk about the basic algorithm of breadth first search with the visited flag. Any idea what the time complexity here? So if we visit one node, we're guaranteeing that we're not going to visit it again because of this Boolean flag. So, yeah. Sorry? O of n, right, where n is the number of nodes in the, number of intersections in the map. So we are basically visiting every node in the graph once, and because of this Boolean flag, we're not visiting it again. And if you notice inside the while loop, the amount of work that we are doing on one node is constant, because it's a bunch of if statements, and there is one for loop that goes over all the outgoing edges. But we talked in the previous lecture that the number of outgoing edges is usually, the average number of intersections connected to one intersection is usually around 4. Okay, so that's considered constant time. And if you multiply by number of nodes, which is n, so that you get O of n. Okay, so it's similar to the depth first search. It's pretty fast, and it usually takes less than 1 second to traverse the nodes in Toronto. So that's a good enough algorithm, but again, it won't get us the best path or the most optimal path. So we need to do something better, and we try to look at the re-expansion algorithm. So any idea what the time complexity of the re-expansion algorithm? Now we are not marking nodes as visited. We might visit them again. So anyone wants to take a shot at this? It's difficult. So it's actually difficult to bound because we don't know how the graph is constructed. We don't know the travel times of all of the nodes, edges in the graph. So we might keep visiting nodes over and over again, and we might visit the whole graph more than once. So it's hard to actually put a bound on the time complexity of this algorithm, and it might be really slow if we are out of luck. Okay? So we need a way to limit our, we were going to demo this later on at the end of the lecture, but we need to limit the expansion somehow, re-expansion somehow, because we don't want to visit the nodes over and over again. So let's go back to this paper map, and what we are doing in the breadth first search is that we are constructing wavefronts of certain radiuses and then expanding them over one by one until we are able to find the destination intersection. With the re-expansion, what we are doing is that we might visit nodes again and construct wavefronts from those nodes over and over again, right? So you can see that we are doing a lot of wasteful work because we are visiting nodes that we don't even need to visit once. We are visiting them more than once because this is how the algorithm is constructed. Okay, so the current data structure that we use to populate the wavefronts is a linked list. You can also use a queue. But all of this falls under what we call FIFO, first in, first out. So the first element that we push to the wavefront is the first element that we're going to visit, right? And there is no certain order in this. It's just like whoever gets pushed first will be pulled first. So in the previous graph, for example, you notice that because we visited 1 before 2, we ended up having to re-expand from 1 because 1 was visited first. Okay, so anyone has any idea how to tackle this? Is there some kind of data structure that we can use, or some kind of like some tweak to this algorithm that we can do in order to limit our expansion somehow? We don't want to visit nodes over and over again that we don't need to visit. So basically, is there some kind of a tweak we can do on this algorithm, the breadth first search with the expansion, or some kind of data structure that we can use that will help us limit the number of nodes that we are visiting or re-expanding from. So first, do you understand that there is a problem with the re-expansion? Why is it slow, right? Right? Okay, so we need some kind of a tweak to do in order to limit that thing. We want to avoid re-expanding from nodes somehow, while still achieving optimality and trying to achieve the optimal solution. No? So what do we notice here in this? So this is the FIFO that we are using. This is the linked list we're using. We pushed node 78 with 20 seconds first, right? This is the 20-second travel time. After it, we pushed node 2 and with 5 seconds. So because we pushed node 78 first, we're gonna pull it first and visit that node travel time first, right? Okay. We might, later on, we might push 78 again with a less travel time somehow, right? We're visiting it from another node. So intuitively, what can we do here? Like, where do we need to start out of these 3 nodes first? Let's talk about these 3 nodes. 2, right. So intuitively, we start with 2. It has the minimum travel time right now from the candidate pool that we have, right? So why not start from there? Because at least it guarantees to us that this is the minimum travel time we can have out of all the candidate nodes right now. So we need to change our insert and remove from the wavefront in order to minimize the node re-expansion by thinking of ways to, let's say, trying to remove the nodes with the minimum travel time first, right? Okay, so let's follow that idea. Let's take the smallest travel time first. Back to our graph. We are pushing node 0 with 0 seconds because it's the source, right? And then when we push node 1 and 2, we are pushing node 1 with 15 seconds because it's reachable from 0 that way, and node 2 with 5 seconds. Okay, because 2 has smaller travel time, we're going to start from it. Right now we don't know how to do that, right? It's fine. We're gonna talk about it. Let's just try to intuitively solve the graph as is by hand. Okay, so we pull 2 first, and 2 is visited, it takes 5 seconds. It has 1 outgoing edge, which is node 1, so we're going to push 1 again with 10 seconds. Now we have 2 node 1s in the wavefront, 1 with 15 seconds and 1 with 10 seconds. What do we take? We take the smaller one, which is 10 seconds, right? So we took 10 seconds, we push node 3 with 16 seconds. Now, when we visit, now node 1 has smaller travel time than node 3 in the wavefront, right? So we're going to depopulate it, we're going to remove it, but now notice that the overall travel time to node 1, sorry, go ahead.
Can you use a set?
Yes, we're going, you're on the right track. So, so right now, node 1 we know that the best travel time to reach node 1 was 10 seconds already, so we don't need to do anything with this one in the wavefront because it has 15 seconds, it's more than 10 seconds. So we just throw it away, we don't visit it again, and we continue removing from the wavefront 3 and then 4, and then we found the best times, the best travel path, which is this, and we didn't have to re-expand from anywhere. Why? Because we always took the smaller travel time first. That makes sense? Do you understand why this works? Like why taking the minimum travel time, minimum candidate travel time for any candidate in the pool first? Okay. And this is a popular algorithm, so it's a small addition to the breadth-first search. Instead of visiting the nodes in a FIFO manner, we just visited in some other fashion where we take the minimum travel time first. And this algorithm is called Djikstra. It's a very popular algorithm. It's named after the person who invented it. And it's a like building block for different kinds of graph algorithms. We use it a lot in industry. Okay, so now we need to think about the data structure that allows us to do this. So your friend here alluded to one of the ways to do that, which is a set. We're going to talk about it. But let's first start from why can't we use linked list? So remember, we need a way to be able to search in the candidate pool right now in the wavefront for the node with the smallest travel time. So what's the insertion complexity of a linked list? It's O of 1. So you can just directly insert a node. This is why we're using a linked list from the beginning, right? You just need to update the next node for the tail. Okay. What is the time complexity to search for a node with the smallest travel time in the linked list? Anyone knows? Sorry? Sorry, I can't hear. O of n, right. So where n is the size of the linked list. So I'm going to introduce another variable called m here so that we don't confuse it with n, which is the number of intersections in the city. Okay? So m here is the size of the candidate pool or the wavefront that we have. So we need to scan the entire wavefront right now in order to find an element with the smallest travel time. The problem is that m can be up to n. It can be the whole graph. Usually, that's in the worst case. Usually it's around square root of m because you're only taking radiuses of nodes and then removing nodes that you visited before, right? So it's usually you can approximate by square root of n, okay? But that's still a lot because now we are doing, let's say take the worst case, which is O of where m is equal to n. And remember, we are visiting in each node in the breadth first search at least one. Okay, so if we do this in each iteration and trying to find the minimum node with the minimum travel time, now we're having an overall time complexity of O of n squared. Okay, and that's huge for cities like Toronto, Tokyo, whatever. It will take you probably hours to finish the algorithm. So it's obviously not a good data structure. So we need a better data structure to insert remove from the wavefront. Okay, so your friend here said a set is one of these. What is the implementation of a set? Do you know? Yeah, like what is it under the hood? What is it? How is it implemented under the hood? Like what is the base data structure of a set? Do you know? You covered this in 244. Okay. Yes, it's a binary search tree. So in 244, you took binary search trees, and remember that binary search tree guarantees that nodes are in order because all of the nodes in the left subtree are smaller than the current node, and all of the nodes in the right subtree are greater than the current node. That's one way. We're going to talk about it, but anyone can think of any other. You might not have heard of it yet, but yeah, go ahead, B07. A min heap, right. So what is a min heap, do you know?
Like the smallest element is always stored at the root of the heap.
Okay, yeah. So a min heap, your friend here suggested a min heap. You might not have heard of it yet, which is fine. A min heap is another data structure, which is a tree-like data structure. It's kind of like a binary search tree, but it's partially sorted. It's not fully sorted as a binary search tree. And in C++, you can use this as a min heap, or you can use something called priority queues. Priority queues are, you can use them from the queue header, and they are implemented under the hood as min heaps. We're going to talk about it, and this is probably the best that you can do for Djikstra, the min heap. It's a little bit better than binary search tree, and we're gonna see why. Okay. So let's talk about first using a binary tree or a binary search tree. So in a binary tree, remember, the insertion time to insert into a tree is log m, right? So right now we're doing a little bit worse than linked list in terms of insertion. Instead of O of 1, we're using O of log n, or m. But to remove as well, we need O of log m, right? So if you do the overall complexity, we know that a linked list takes O of m, which is usually O of n, square root of n, or O of n, while a binary tree takes O of log m. Log m is usually less than or equal to log n, because we know that m can be much smaller than n, right? So the overall complexity of the breadth first search algorithm, with linked lists, we talked about it, is gonna take O of n squared on average, in the worst case. In binary search tree, it's going to be n log n. N is the number of nodes in the city, and in each iteration we are doing log n work to remove from the data structure. Yes, Don.
Can you explain what each of those complexities are referring to? So you're saying the square root n for a linked list is for removing, and then where do you get the n squared from?
Yeah, so, okay. So right now we are talking in terms of the size of the data structure that we have is M, not N, okay? Because N is used for the number of intersections. I just don't want to confuse both, right?
So M is not the number of intersections?
No, M is the number of candidate nodes in the wavefront that we're using while traversing the breadth first search, right? Because it can be up to N. You can put all of the nodes as candidate nodes, right? But usually on average, I'm not gonna go into the details, because we are inserting and removing in each iteration, on average, and we're expanding the wavefront a little bit, usually on average is going to be square root of N. So M is usually equal to square root of N, right? Okay, so in each iteration, what are we doing? We are trying to find the node with the minimum travel time in that data structure. So if we're using a linked list, in each iteration we are using O of M or O of square root of N work, right? Okay, and because we are visiting each node at least once, we need to do this for every intersection in the city, and that's where the O of N squared comes from, or O of N to the 1.5, if we are assuming it's square root of N. Does that make sense?
So you're squaring the square root?
You're multiplying the number of nodes by the time complexity of one search in the data structure. So if let's go back to the algorithm, right? Yeah, here. Now we need to update the, in order to populate from the data structure, we need to find the node with the minimum travel time first, right? Because that's how Djikstra works right now. We want to limit the re-expansion. So we said that to do that in a linked list, you need to go over all of the linked list. You need to visit every single node in the linked list. So this is O of M. M is the number of nodes in the candidate pool, right? We said that M is usually going to be around either square root of N to N. It can range between square root of N to N. Okay, let's assume it's N, forget about the square root. So because if it's N, that means in each iteration we are doing O of N work, right? And how many iterations are we doing? We are visiting at least each node once in the graph.
Yes, N times N.
So N squared.
Yeah, I'll get with N to 1.5.
It's basically the, if you, okay, so we said that N is the worst case for M, right? But on average, we said that usually the number of nodes that we're going to visit next, or the candidate nodes, are usually on the order of square root of N, N to the 0.5, okay? So now the amount of work that you're doing in each iteration is not O of N, it's O of N to the 0.5, right? If you multiply that by the number of nodes in the city, you get N to the 1.5.
So you're multiplying O to the N.5 with
N. Okay, and that's the overall complexity of the whole algorithm, not just one iteration. Does that make sense?
Yeah.
Okay. Now, again, we said that Toronto has around 100 to 200,000 nodes, and if we assume that each iteration is going to take 10 to the -7 seconds, that's usually 3.2 seconds to 1,000 seconds, depending on how big the candidate pool is, right? And that's obviously not a very efficient algorithm. Okay, so if we use a binary tree, on the other hand, a binary tree takes log m, and remember, log m is way less than or equal to log n, because m is less than or equal to n. So the overall time complexity of breadth first search, is going to be less than 1 second. And that's much more efficient than using a linked list. Is that clear? Any questions? Okay. So anything faster than binary tree. So remember, a set, if you're using a set, it's the same implementation as a binary search tree. Now, your friend here talked about a min heap. What is a min heap? Again, a min heap is very close to a binary search tree, but it has one single difference. The element on the top, or the element on the root, has to be less than or equal to all of its children, right? So we say that this node is this tree is partially sorted, not completely sorted. It still has the same asymptotic time complexity. It still has insertion of O of log n. It still has a removal of O of log n, similar to a binary search tree. But the absolute time is actually faster by a constant than the binary search tree. And usually that constant is around 3x. So that's a significant amount that is noticeable, and it's usually better to take. So that's why we usually prefer to use min heaps over binary search trees in this algorithm. But the asymptotic time complexity is still the same. It's like log n. Okay? Is that clear? Sounds good. Okay, so how does this work? Again, the key of the parent is usually, has to be less than the key of all of its children for all the nodes in the tree. So for example, in this example, the node on the top is the smallest node, and this is called a min heap. There is something also called a max heap. Some other algorithms might use it, where the node on the top is the largest in the whole overall tree. Okay, so think of this as the travel time of every node in the candidate pool. So when you want to populate, you will just take the node on the top, right? Because we know that is guaranteed to be the minimum travel time. So. And this is called a priority queue. A priority queue is basically, I'm going to insert in a FIFO manner, but to remove, I'm just going to remove always the best metric. That metric you define. In this case, it's the minimum travel time. Okay, so the smallest item is always at the root of the heap. And if you notice here that there is no ordering between the siblings, right? So for example, 40 here is on the left, which is greater than 35, while in this case, 37 is on the left, it's smaller than 60, the right subchild. So between the siblings, there is no specific ordering. The only thing we care about is what? It's that the root or the parent is smaller than its children. Okay, so you don't have to code this data structure from scratch. It's actually a bit complicated to do that, but it's good to know how things work. So how do we remove the smallest item from the tree? So we said that obviously the smallest item is always what? On the top of the tree, right? It's always at the root. So we take that and we pop it off. This is the node, the candidate node that we're going to use next. But now we need to update the tree somehow, because now we have a discontinuity here in the tree and we need to update it, right? So the way we do this, we first move the bottommost element, which is here, 50, to the root, okay? Now, if you notice, it's not a min heap anymore, because 50 is larger than its children. So what we start basically visiting level by level and trying to switch the root with its children until we satisfy the conditions. So we perform what we call a heapify to fix the heap. So we start at 50, compare it with 20 and 36. We usually take the smaller one and we swap it with 20. And then we visit the second level. Now 50, we compare it with 40 and 35. We swap it with 35. And now there is no more work to do, right? We are at the leaf level of the tree, okay? So at most, in any binary tree, we have what? Log n levels, right? So we are doing the swapping log n times. And that's why the time complexity of a removal from a min heap is log n. Okay, the push to insert a new element is kind of the same. I'm not gonna go over it, but basically we usually, we insert at the end of the tree. So we insert a new element here, for example, as a new leaf, and then we do a heapify again by comparing to its parents and try to fix the tree. Any questions on this? Again, you're probably not gonna code this from scratch, but you need to do this, to know this. In OP2, your TA might ask you also questions about this, right? So you have to know how a min heap works. Okay. In C++, there are two ways to use this. In the STL, it provides you with a make heap function for any vector, but I usually prefer to use what is called a priority queue. So you can look it up, and it's under the queue header, and it's a very good data structure to use for your milestone tree. Okay, so now we talked about the breadth first search and Djikstra. Let's do a quick demo to show that why Djikstra is a little bit better than the re-expansion. Actually, it's much better. Okay, so again, this is the golden solution. I showed you this last lecture. So I showed you last lecture, whoops. Why can't I press on this? Yeah, I showed you last lecture the breadth first search implementation of our algorithm, but this is actually not the breadth first. This is the breadth first with re-expansion in order to get the optimal solution, right? So if I click on any intersection in the city, you notice that how it's doing a wavefront, and notice how it found a very good travel time, which is 23 minutes, but it took time. Why? Because it's trying to re-expand. If I click on a further intersection in the city, it's probably going to look, notice how it is very slow to do that, right? Why? Because it's re-expanding over and over again in order to find a better travel time for each node. Okay, so I'm gonna stop this. It's probably gonna take a lot of time. So let's set the algorithm now to Djikstra. So again, all what we did in Djikstra is that we just switched the data structure for the wavefront from a linked list to a priority queue, right? And notice how much faster it is now. So if I press here, it's way faster than a breadth first search in order to find the minimum travel time. Okay, so Djikstra is basically the first good algorithm that you can use for milestone 3 to achieve good results, right? It probably won't achieve, pass the hard test yet, because some of the hard tests we'll cover this algorithm in the next lecture. But you need to do better than Djikstra in order to limit the expansion more and more, and try not to visit all of the nodes that are unnecessary to visit, okay? Any questions on this? Yes? Do you want me to tell you? It's called A-star. A-star.
Oh.
Okay. Have you heard of it?
Yeah.
Okay. So we're going to introduce it a little bit now, but I'm not going to go over the details. I probably won't have time. Okay, so that's a segue to our next topic, which is, can we do better than Djikstra? Why is still Djikstra a problem here? Okay, so let's go back to our paper map and see how Djikstra is working. Remember, Djikstra is a priority queue, uses a priority queue, but we are still defining all of these wavefronts around our current node, right? So we start at the source intersection, and little by little we start expanding, and we saw that from the demo how it's trying to expand. Okay, so if you notice here, we are doing a lot of work that we might probably better to avoid, because intuitively, there's the best travel time to travel from node is going to be somewhere around here, right? Like we're trying to, it's going probably to use the intersections around in this area, in this quadrant. But there is no way around in Djikstra than visiting every single node in all of these, right? So we're still visiting nodes around here. They are not necessary to visit, but we have to visit them. And that's why we're trying, can we achieve better than that? We're wasting CPU cycles on this, and probably better off using that CPU cycle somewhere else, right? So, any ideas? Anyone has any idea, like, just an intuitively, what can we do? I don't care about algorithm names, I just want ideas. Yeah, go ahead, ECE297. Sorry, go ahead.
If you expand it out of nodes, then you have like two smaller circles, like a smaller area.
Yes, and you find the intersection of these. That's a very good idea. So so what's your name? Tune. Okay. So Tune said basically to expand from both ends. Right now we are only expanding from the source, right? So notice here we are expanding the wavefront from the source. Toon said that I'm going to do a reverse Djikstra, for example, and also expand at the same time from the destination. So while traversing both of these usually in parallel, we try to find the intersection between these two, and then this is a way to limit our candidate node list, right? This is probably the node list that we're going to do. So this is a very good idea. I'm not going to talk about it in the lecture, but it's one way to do it, and we actually implemented it in the golden solution. Yes, go ahead.
I think you can also estimate, like, for each node, if it's getting closer to the destination by taking the hypotenuse.
Okay, so what's your name again?
Alex?
Alex. So Alex said that another idea is to try to estimate the distance, or estimate how far are we currently from the destination, in order to limit the number of nodes limit the candidate nodes to those that are closer to the candidate. So for example, maybe these nodes are closer to the destination from these nodes. So I'm going to give them priority to visit them. This is a very good idea. But we have to be careful. Sometimes we miss nodes that we have to visit. For example, so the idea is basically trying to take the node that has a smaller distance to the destination from the other nodes. Okay? But let's take this example. So this example is trying to go from this node to this node, and between them is a highway, right? So we need to go over to cross the highway somehow in order to go there. And the only way to do this is to go through this path, right? To go through here, and because here also there is no intersection that goes to the destination, so we have to loop around. If we only care about the nodes that are closer to the candidates, we might end up removing the nodes that we have to visit, right? So we have to be careful on how to choose the candidate set to visit. But this is on the right track. We need some kind of what we call a heuristic in order to limit our search space in Djikstra. But at the same time, still guaranteeing that we're going to visit the nodes that we have to visit. Okay. So this is what I have for this lecture. We're going to continue talking about this. This algorithm is called A star. And this probably you need to implement some kind of a version of it to pass the very hard test in this milestone. Okay? We still have 3 minutes. If you have any questions, I'm happy to answer. If not, yeah. See you next week.
For the original one, where we just said normal BFS, instead of O and, I'm just trying to understand how that works, because even though we set a visited flight, say we're not going to look at it again, all the operations of that visited flight is still constant, because all we're doing beyond that if not visited flight is we're just getting the time,
Getting the neighboring edges and pushing
away from and if the for loop is just like for, or it's like it's constant, then how is that actually adding to, if that, like what I'm trying to get at is, if the only part that makes it O(n) is the fact that we're